So recall that at the moment we are in TP2 theories. We're doing a week of that. And last time we proved that basically we proved that you can reduce formulas with TP2 to one variable. So let me state the precise thing that we said, theorem. Chernikov. What we proved last time was either well, okay, suppose there is an I in P pattern of size kappa 1 times kappa 2. Or sorry, I shouldn't say size. The adjective we used was depth. Of depth kappa 1 times kappa 2 in the type of B1, B2 over C. Then either there is an I in P pattern of size kappa 1, kappa 1 in the type of B1 over C, or an I in P pattern of, and again I said size, and I should have said depth. It doesn't matter. I mean, Shalad defined I in P pattern, but he didn't define this cardinal kappa, which we're calling the depth. So Artem wrote a paper and he called it depth, and then I wrote a paper and I called it height, without paying attention. And then I refereed a paper recently that called it width. So I guess you can either, I don't know which dimension you're going at. I mean, people are confused. I guess it depends on how you draw the picture. So okay, you can call it whatever you like. Size makes sense, but 9p pattern of depth kappa 2 in the type of B2 over B1C. So these are the options. And let's just recall how the proof went. So we start with a really big array. And the height of this array is kappa 1 times kappa 2. And then we break up this array into a bunch of pieces. So each piece will have size kappa 2, and there are kappa 1 of them. So the idea is, like, you think about kappa 1 times kappa 2 being ordered lexicographically. That means for each alpha in kappa 1, you have kappa 2 many things, which are sort of its associated y coordinate. And so you can sort of break up this array into a bunch of pieces. Then we had this lemma that says, if you have some type and there's no I in P pattern of depth kappa in it, then whenever you have a mutually indiscernible array of height kappa, you can move one of the rows to become indiscernible over a realization of the type. So the idea is we first look at I guess we first look at the type of B2 over CB1. That's the one where we know that we don't have something of size kappa of depth kappa 2 in it. So we look at this one and we move it to become indiscernible over B2 and C. And then we look at this one and we move something here to become indiscernible over B2C. And we look at this block and we move something here to become indiscernible over B2C. But when we're moving it to become indiscernible over B2C, we also move it to become indiscernible over B2C and all of the other stuff. That's part of our induction. So what we're doing is, as we do this inductively in kappa 1 many steps, what we've done is we've constructed a mutually indiscernible array of height kappa 1, taking one row out of each one of these arrays of height kappa 2, which is mutually indiscernible and what is it mutually indiscernible over? It's mutually indiscernible over C B2. So you've made it indiscernible not just over B1, but over CB2. And then now you have a mutually indiscernible array over CB2, and we were told that yeah, here I think maybe I should have switched B1 and B2. Okay, it doesn't matter. We know that there's no there's no mutually indiscernible sequence of depth kappa 1 and CB2. I think that's how I should have said it. So so let's say it this way, of kappa 1, oops, in CB2, or kappa 2 in this over C. That's actually what it seems like we're proving. And okay, now we have a mutually indiscernible array over CB2. So we just say, again by the lemma, I can find one of these rows and move it to become indiscernible over CB1. So what does that mean? Well, our lemma tells us that that means that there's no, this sequence now, which is indiscernible over CB1 and B2, witnesses that there's no mutually indiscernible array of height kappa 1 times kappa 2. What did we need to do? We needed to find one row in our massive array, which could be moved to become indiscernible over B1, B2. So in the first step, we found a mutually indiscernible array, which is of height kappa 1 and mutually indiscernible over CB2. Then we move one of those rows to become indiscernible over B1 and CB2. That's the same thing as moving one of the rows to become indiscernible over CB1, B2 from the original array. And that meant that it contradicted our assumption that there was an INP pattern of depth kappa 1 times kappa 2 in the type of the pair. So there are two important corollaries of this, which I want to draw out. So the first one comes from this notion of burden. So here's a definition. So suppose P is a type. The burden of P is the supremum of the depths of I in P patterns in P. Okay, so you just look at what kind of INP patterns you can have. And okay, in the context of simple theories, there's a notion called weight. And this is related to weight in TP2 context. So someone needed a word that sounded like weight. And okay, what is it like to carry a weight? Well, it's a heavy burden. So that's where the name burden comes from. I can't remember if it was Artem or Hans Adler that defined this, but okay, it was one of those two. Okay, so this is some rough notion of dimension. So for example, if you have a tuple of variables, x equals x0 through xn minus 1, then the burden of x equals x is always at least n. Why? Because for example, you can build an INP pattern where you say you have a formula like x0 equals y and x1 equals y, or sorry, that says y1. Sorry, this should say x1 equals y, x2 equals y, and so on and so forth. And just choose a bunch of mutually indiscernible indistinct elements, and distinct elements. So of course, saying that the first variable is equal to this, and the second variable is equal to this, and the third variable is equal to this, these are all independent, right? I mean, there's no constraints on setting the variables equal to things. But of course, if the elements are distinct, then as I move across the rows, I'm getting two inconsistent rows, because I can't say that xi is equal to A and xi is equal to B if A and B are distinct. So this example shows you that you can always build an INP pattern of depth at least n if you have n free variables. So that tells you that it's like kind of related to the number of variables you're looking at. It's kind of related to the dimension. And sort of a corollary of what we proved is that burden is submultiplicative. So if you compute the burden of type B1, B2 over C, this is less than or equal to the burden of, okay, type of B1 over CB2 times the burden of the type of B2 over C, which is an immediate consequence of what we proved. Right? I mean, yeah, I mean, it just follows. So there's a major open question. So main open question is it sub-additive? So what should that mean? That should mean that you can replace with plus. All right. Now, why is this interesting? Well, there is this class of theories called NIP theories. And there's a related notion closely related to burden called DP rank, which sort of tells you how many independent instances of something like of kind of like independent behavior. So the question in the context of NIP theories was, can you classify all DP minimal fields? And this was something that Will Johnson did. He sort of gave an explicit classification of DP minimal fields. And then there was a much more difficult and longer body of work that classified the DP finite fields, which are the fields that have finite DP rank. And sort of the natural next step is to prove this for I and P minimal fields. That is the fields that have burden 1 and finite burden fields. Okay, but if you only know that burden is submultiplicative, many of the dimension theoretic arguments that people had in mind just simply don't work. It's not strong enough. So if you could answer this question, many people would be happy with you, and it would be a real achievement. So, I think since most of you are graduate students at UCLA, I should tell you that, okay, if you wanted a project, this would be a great one to work on, and Artem would be very happy if you did. Okay, so that's one consequence, and a second consequence. So what is the next consequence? The next consequence is that if T has TP2, then this is witnessed by some formula. Oh, really scared me. By some formula in a single free variable. Okay, why? Well, okay, if phi x, y, z has TP2, then it follows that then there's an array let's say a alpha less than t plus, I less than omega, witnessing this. So what do I mean? Let's recall what it means to have TP2, right? It means that you have this mutually indiscernible array where any way of snaking through the array is consistent, but the rows are k inconsistent for some fixed k. That's what it means to have TP2. So that means that we can let B1, B2 realize the all zeros path, let's say. So phi x, y, a alpha 0 as alpha ranges over t plus. So what we know is that the burden of B1 times B2 over the empty set, by which I mean the burden of this type, is therefore at least t plus, which really means that it's equal to infinity. And that's, of course, the same thing as t plus times t plus. So that implies that either the burden of B1 over B2 is at least t plus, or the burden of B2 is at least t plus. So if we know that, then that means that in one of these types, there has to be an INP pattern of height t plus. But what does that mean? If you have an INP pattern of height at least t plus, then there has to be cofinally many levels with the same formula and cofinally many levels with the same k. So it follows that you can find a formula witnessing TP2 with fewer variables. So it started with x, y as your tuple of variables, and then you could reduce it either to x or reduce it to y. So by induction, eventually you can reduce it all the way down to 1. So whenever you can do it in a tuple of variables, which you can break up into two pieces, then you know that you can reduce it to one of those two pieces. That continues until you get down to 1. All right, so that's super useful in concrete structures. You can imagine like you have some particular structure like coming from algebra or combinatorics, and you want to check, okay, by hand, does it have TP2? Well, if you know that you only have to look at formulas with one free variable, oftentimes that is like a helpful reduction in the complexity of this problem, because maybe you can have greater control over what the formulas in one variable look like. So this gets used quite a bit. Okay, so now we're going to move on to a topic with a somewhat different flavor, which is forking and dividing in TP2 theories. Actually, the red is not very pretty. Let's pick something like dark purple. All right, so let me just fix some definitions. So I can't remember if I defined it in this class, so I'm going to write it this way. So if I have A, B, and M, let's say M is a model of the theory, then this means that the type of A over MB extends, so this holds if and only if the type of A over MB extends to a global M invariant type over M. So this is one way in which these are independent. And just note as an exercise, ind I implies ind F. So if you have the property that the type of A over MB extends to a global M invariant type, then you cannot fork. And this is an exercise. Okay, so this is easy to check. I encourage you to do it. And then we're going to have two notions which are sort of built out of invariant types. So the first is the notion of an invariant or an indiscernible type. So suppose AI, I less than omega, is an M indiscernible type. Sorry, M indiscernible sequence. We say Q extending the type of A bar over, so I'm going to call this whole sequence A bar. So I take some type which is a global M invariant extension is an indiscernible type if whenever B is a set of parameters, say containing m, and A bar prime realizes Q over B, then A bar prime is B indiscernible. So what's the idea? Here, I think I might be able to switch this so you can see more. The idea is we have some small model, M, and we look over the entire monster. So here we've got our monster model, and I've got some indiscernible sequence. So then I extend to some larger set of parameters, B, and I realize the type over this larger set of parameters. I want this realization to be indiscernible over B as well. This is equivalent to saying that if I realize the whole global type, like in some bigger monster model, over the entire monster, it's indiscernible over the entire monster. All right, so why should that exist? Well, we'll prove that they exist, and it turns out to be not so difficult. So you can build these sequences or build these types such that realizations are indiscernible over any set you look at, which is nice to know. So the definition here is for that of an indiscernible type. So the way you should think about it is it's just a type that generates indiscernible sequences. If I realize it over any set, I get an indiscernible sequence over that set, which is useful. Okay, cool. So that's one notion. And then the second notion is a global invariant type Q is called strictly invariant over M if whenever B contains M. So this is like before, whenever B contains M and A realizes Q over B, we have B is non-forking independent over M with A. Okay, so what does this say? Let's remember how things look in simple theories. So in simple theories, we know that if A is non-forking independent with B, then automatically B is non-forking independent with A. You have symmetry there. Now, symmetry characterizes simple theories. If you have a theory in which forking is symmetric, the theory must be simple. That's a theorem. We didn't prove it, but it's true. So what you should think of is a strict invariant type is a type which recovers just a hint of symmetry. So you have invariance going one way. So when you realize A over B, because invariant independence implies non-forking, you have that A is non-forking independent with B, but also you have that B is non-forking independent with A. So one of those directions follows from the fact that just Q is a global invariant type. And we said before that ind I implies ind F, right? Like that was a remark I made above. But then this says that actually you can switch, at least with non-forking. So you don't get invariance both ways, but you get invariance one way and non-forking the other. And this is some way of like recovering a hint of symmetry. I mean, it does imply that you're forking both ways, but it's a bit stronger than that. You have invariance one way and non-forking another. All right. And a strict invariant Morley sequence over M is a Morley sequence over M in some global M invariant type. Okay, so if you recall, whenever you have a global M invariant type, you can use this to generate a Morley sequence. You realize it once over the base, over n, let's say, and then you realize it again over m and the first realization, and then you realize it again over m and the first two realizations, and you realize it again over m and the first three realizations, and so on and so forth. And that always gives you some indiscernible sequence. And okay, if the global M invariant type that you were looking at happened to be a strict invariant type, then you would call it a strict invariant Morley sequence. All right, so these are sort of like the basic tools for understanding how to understand forking and dividing in an NTP2 context. And I should say that there's a kind of philosophy to this, which is you had Kim's lemma in simple theories. And what did Kim's lemma say? It said that if I wanted to understand when formulas divide, I have to just look at its behavior along sufficiently generic sequences. I had this notion of a Morley sequence where it was indiscernible and the ith element was forking independent over everything that came before. And if the formula was inconsistent along such a sequence, then it divided. And if it divided, then it was inconsistent along such a sequence. That's what Kim's lemma said. Now, that equivalence between dividing with respect to Morley sequences, like every Morley sequence, and dividing is something that characterizes simple theories. So you can't expect that to be true outside a simple context. But what you could try to do is to recover the same equivalence by looking at an even more generic kind of Morley sequence. So, okay, so knowing that you divide is not going to be the same thing as dividing with respect to every Morley sequence. So you might want to narrow the class down to an even more generic notion of sequence and hope that you recover the equivalence once more. So that's going to be one way of generalizing simple theories to a non-simple context. You look at a more generic kind of sequence and then hope that you get the same Kim's lemma. And that's exactly what's going to be true in NTP2. We're looking now at a stronger form of Morley sequence, these like strict invariant Morley sequences, and that's going to characterize dividing, and we're going to get Kim's lemma, and as a consequence, we get that forking will equal dividing in NTP2 theory, which is one of the best things we know about NTP2 theories. And I should say that there was a question, which I guess was asked around 2004 or thereabouts, which was whether or not forking equals dividing in NIP theories. So recall we learned about the independence property where you can code sort of arbitrary subsets. And you have this class of theories called NIP theories. And there was just a question, is forking equal dividing in that setting? It was, of course, known for quite a long time by that stage that that's true in simple theories. And so that's the next natural candidate. And I think either 2006 or 2007, there was this paper by Itai Kaplan and Artem Chernikov proving that forking equals dividing, not just in NIP theories, but in NTP2 theories. And somehow NTP2 was like the right context in which to understand this problem, because there everything became clear. And that was like a real shock, I think, to many people in the model-theoretic community, because it was one of the few instances where you take a really simple class like NIP theories, and you actually solve a problem there by looking at a much general class where you can just sort of see very clearly what it is that you have to push against. So that's the theorem that we're going to prove, and then we're going to move on to a different class of theories. Okay, so let's start proving some stuff. So the first thing I want to prove is just that indiscernible types exist. So here's a lemma. So this requires no assumptions. It's true in every theory. So suppose M is a model of your theory, and Q, or sorry, let me say the name of the sequence. AI, I less than omega, is a M indiscernible sequence. Then there is a global M invariant indiscernible type. Q, extending the type of A bar over M. Okay, so I'm going to give just a few of the details because I think you'll see how the argument goes very quickly. So here's the proof. So let R, extending the type of A bar over M, be a global M invariant type. So we proved long ago that whenever you have a type over a model, you can always extend it to a global M invariant one. And we even gave an explicit construction of how to do this. You can take an ultra filter on the model whose average gives you the type, and then you can use that same ultra filter to define a global extension. So you can look at like avd over blackboard bold M, and that'll give you some global M invariant type extending the whole thing. So of course, if I look at the type of A bar over M, that's a type over a model, it's going to have some global M invariant extension, although there's no reason to believe in advance that this R will be indiscernible. So we have some global M invariant type. Now we want to convert it to an indiscernible one. How do we do that? So what we'll do is we will let N extending M be an M plus saturated model. And then we will take a realization over N. So R over N. Okay, so now what we'll do is we will let B bar prime, which, I'll list the elements like B prime I less than omega, be an indiscernible sequence realizing the EM type of B bar over N. So this is the very first theorem we proved in this class. So we have some sequence. We extract an indiscernible sequence from it. So let's just draw the picture. We've got our monster model. Sitting down here, we've got M, and we start at the beginning with some indiscernible sequence, which we are calling A bar. This is the data at the beginning. Then we extend a bit further to get some model N. And we take some sequence that realizes the type of A bar over M. So that sequence, of course, will be M indiscernible, but there's no reason to believe that it's N indiscernible. So then what we do is we extract a third sequence, B bar prime, which is now indiscernible over N. The problem is that we don't know that the type of B bar prime is invariant. So let's just check that it is, and then we'll be done. So claim type of B bar prime over N is M invariant. So why? Suppose not. Then there is a formula phi, which maybe suppresses parameters in M, doesn't matter, and two tuples, C and C prime from N. So I'll draw them here in our picture. We're going to have two points. So this is like C and this is C prime, which both have the same type over N, such that for some I0 less than dot 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 less than I n minus 1, which I'll call I bar, we have phi B I bar C if and only if not phi b I bar C prime. So let's recall what it means to be invariant, right? What it means to be invariant is that if two tuples have the same type, then I put one in as a parameter for phi if and only if I put the other one in as a parameter for phi. So what does it mean to be not invariant? It means I can find some formula, two tuples with the same type, such that one instance of phi goes in and and one instance of the negation of phi goes in. So I have two things with the same type over M, but the rule for when formulas go into the type is not dependent just on that type over M. Okay, that's what it means to be not invariant. So I can find something like this. I can find some finite piece of my indiscernible sequence and two tuples with the same type over M, which disagree about whether phi should go in or not. All right, but because C and C prime are tuples from N, and oh shoot, these should have primes here. I'm sorry, because remember this is in our indiscernible sequence. So remember, we're trying to prove the type of B prime over N is M invariant. So because C and C prime are in N and B bar prime realizes the EM type of B bar over N, there is some J0 less than dot 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 less than Jn minus 1, which I'm going to call the sequence J bar, such that the same is true for that sequence. So we have B J bar C if and only if not phi B J bar C prime. So what does that mean? That means that our original sequence wasn't realizing an invariant type. So if I look at type of B bar over N, that is not M invariant. That contradicts the fact that B realizes R over N and R is M invariant. So this is really just a fact about what the EM type can tell you, right? If you take an indiscernible sequence and you look at a model and you extract an indiscernible sequence from it, because the original sequence realized an invariant type, the indiscernible sequence you extract will also realize an invariant type. Okay. Moreover, okay, so what we'll do is we will let Q, extending the type of B bar over N, be the unique global M invariant extension. This is the extension we want. Okay, so we saw this earlier in our earlier discussion of invariant types. If you extend a type to an M plus saturated model, then there's a unique way of extending it to the monster model. Why? Well, because in order to know whether or not I put phi x c into my type, I just need to know whether or not I put things with the same type as c into my type as parameters in phi. So if I want to know whether or not to do that for any parameter c, I just need to realize the type of c inside M, which I can do by saturation, and then look for the realization in N, whether I put that in the type or not. So in this case, once I know how the type is defined on an M plus saturated model N, I know how to extend. And so this will have a unique extension, and that will also be indiscernible. So I won't write it, but let's just think very quickly, why is it indiscernible? Well, take some really big set, and suppose that you realize the type over that set, and you're not yet indiscernible. You're not indiscernible. So what does that mean? It means that you can find two increasing n tuples and some parameter such that a formula with that parameter says yes to this and it says no to this n tuple. Okay, but if that's true, then you can take the type of the parameter over M and realize it inside of N. By invariance, that means that there's going to be some formula with this new parameter inside N, which says yes to this n tuple and no to this n tuple. And so you can distinguish them over N if you could distinguish them anywhere by invariance and the fact that, by invariance and the fact that N is M plus saturated. And the fact that you took B bar prime to be, prime, prime, you took B bar prime to be N indiscernible meant that you couldn't distinguish them over N, so you can't do it anywhere else. Okay, so this is the indiscernible sequence we want. And that's fantastic because now we can prove what I think will be the main lemma for today, which is that if T is in TP2 and phi x b divides over M, this will be witnessed by some Morley sequence in a global M invariant type. So let me fix that. Morley sequence over M. Okay, so how does this go? So the proof is pretty cool, and I think it sort of shows why these indiscernible types are useful. Okay, so proof. So suppose not. And what we'll do first is we will let B bar, which is Bi, I less than omega, be an M indiscernible sequence with B0 equals B, witnessing that phi xb divides. Okay, so this we can do just by the definition of dividing. We can find some sequence along which the formula is inconsistent. So what does that mean? I.e. phi x bi, I less than omega. It's inconsistent, but the sequence is indiscernible, so it's k inconsistent for some k. Okay, so that's a great place to start. Now, what we will do next is we will let Q, extending the type of B bar over M, be a global M invariance a global M invariant indiscernible type. And we know that these exist by the lemma we just proved. So by induction on n less than omega, we will prove, or let's say n greater than or equal to 1, we will prove that if B bar I less than or equal to n, realize Q tensor n over M, then B bar I, which is my notation for Bij, as I ranges from the numbers 1 through n and j over omega. So this is like an array of height n and width omega, is mutually indiscernible. over m. So how does this work? So I'm realizing my type inductively. So here's like b bar 0, b bar 1, b bar 2, b bar 3, b bar 4, and so on and so forth. So for n equals 1, there's nothing to show. I mean, it is the type of an m indiscernible sequence. So of course, if I realize it once, I get something which is a mutually indiscernible array of height 1. What is that? That's the same thing as an indiscernible sequence. So if I only have one sequence, if I only have one row, then of course, if it's an indiscernible sequence, then it's an indiscernible array. So I haven't said anything at all. So now assume for n, and let b bar n plus 1 realize q over m together with the first n rows. Okie doke. So because what? Because q is indiscernible, we know that b bar n plus 1 is m b less than or equal to n indiscernible. That follows just by the definition of indiscernible type. We take a bigger set, we realize it over the bigger set, then you're automatically indiscernible over the bigger set. That's what's cool about indiscernible types. However, if we take some I, which is less than or equal to n, then because then by induction, we know b bar I is indiscernible over what? It's indiscernible over b bar less than I, and then b bar I plus 1 all the way up to b bar n. That's what the inductive hypothesis told me. So what does it mean to be mutually indiscernible? Being mutually indiscernible means that if I fix one of the rows, then that row is indiscernible over all the other stuff. So if I have a mutually indiscernible array of height n, then if I fix the ith row, then I'm indiscernible over the stuff that comes below. That's like b bar less than I, and the stuff that comes above. That's like b bar I plus 1 all the way to b bar n. And I want to know that I can add b bar n plus 1 to the top. Okay. And since q is invariant, m invariant, it follows that well, okay. It follows that because b bar n plus 1 realizes q over all this stuff, b bar I is additionally indiscernible over the whole thing, m b bar less than I, b bar I plus 1 all the way up through b bar n plus 1. Let's think about why very quickly. So what would it mean for this not to be true? What it would mean for this not to be true is that you have some formula and two increasing intuples from b bar I, together with some parameters from all this other junk, like b bar less than I, b bar I plus 1 all the way up through n, such that, one of those formulas holds with parameters coming from b bar n plus 1, and the other formula doesn't hold with the parameters coming from b bar n plus 1, right? I mean, this is what it means to not to be indiscernible. But those two types, I mean, the two parameters have the same type over M, and what you're saying is that one goes into the type Q, and the other one doesn't go into the type Q. And that's not possible when the type is M invariant. So the fact that you're indiscernible over M and this other stuff, and then you realize a global M invariant type over that other stuff means that you're indiscernible not just over the stuff, but over the new realization. You're indiscernible not just over B bar less than I, B bar I plus one all the way up to Bn, but additionally you can add B bar n plus one there too. So if you generate along this type, you get a mutually indiscernible array. Okay, so let B bar I less than omega, be a Morley sequence. So anyway, that's the proof of the claim. Be a Morley sequence over M in Q. Then what does our picture look like? We've got a whole bunch of rows. So each row is, this is K inconsistent. Why? Well, because each one of the rows has the same type as B bar over M. I mean, Q is a global extension of the type of B bar over M. So they all have the same type as B bar over M. And I was told that B bar is the sequence that witnesses that my formula divides over M. So the formula was K inconsistent along that row. So it has to be inconsistent along all these rows because they all have the same type. And the type will tell me that, okay, this formula is inconsistent along this row. Okay, but what was my hypothesis? Towards contradiction, I assumed that my formula did not divide with respect to Morley sequences in any global invariant type. What happens if I look at the all zeros column of my array? If I look at the first column in my array, that comes from a Morley sequence in a global invariant type. It's a Morley sequence in one of the projections of Q to like the first variable. It's a Morley sequence in Q, or it comes from a Morley sequence in Q. It's a subtuple of a Morley sequence in Q. So it's a global M-invariant type. But I've assumed that my formula does not divide with respect to any such sequence. So that means that the all zeros column is consistent. That very first column is consistent. Otherwise, it would be, otherwise this would be a Morley sequence in a global M-invariant type, which witnessed that my formula divided, and I assumed there was no such. But this is not any array. This is a mutually indiscernible array. So if I know that one column is consistent, then it follows that actually any way of snaking through my array is also consistent from mutual indiscernibility. So what have we found? We have found that for every function from omega to omega, phi x bi f of I less than omega, is consistent. That follows from the fact that the all zeros column is consistent because it's a Morley sequence in a global invariant type. And we've found that for every I, phi x bi j, I less than omega, is k inconsistent. And lo and behold, that implies that phi witnesses, okay, witnesses TP2, a contradiction. Okie doke. So this is a kind of approximation to Kim's lemma. This says that if you divide, then that will be witnessed by some very generic sequence. But that only gets us half of the way there because, okay, if you know that you're dividing, then you're witnessed by some very generic sequence. Now you want the class of sequences where you can say all. You want to say every generic sequence of a particular kind will witness the dividing. And this just gives us one. So that's what we're going to finish next time, and then that'll be it for TP2. So I'll stop there. Are there any questions that people would like to ask?
I have a small question.
Sure.
Did I mishear you earlier? I kind of, were you saying, so it's known that an NIP theories forking equals dividing? Did you say that?
over models, or
Over models. Oh, okay, okay,
in fact, over extension bases. It's enough.
okay, okay. That
But
that was. I think I missed the over models part.
yeah,
I
no.
was
In fact, it's known that it's false
right,
in general because, of course, the circular order that we've discussed,
right, right.
where you break up the circle into thirds, um, is an NIP theory. In fact, that's interpretable in the real closed field. So it's a very nice NIP theory even, and yet forking doesn't equal dividing. So I mean, so the real question, I mean, right? I think I maybe didn't say it explicitly. The real question is, does forking equal dividing over models? And then the outcome of what Artem and Itai Kaplan did was that forking will always equal dividing over extension bases, meaning in NIP theories, meaning those bases in which sets do not fork over their domain.
Hmm. And did you say that forking equals dividing over models characterizes NTP2? Is that
No.
is that no? Is that known or something like that known?
Um, well, I guess it's known to be false because certainly there are
Hmm.
examples where forking equals dividing and you have TP2.
Oh, I suppose if you just take like the disjoint union of like a really bad NIP theory and a really bad, well, quote unquote bad simple theory, or I don't know, like is there a simple example like that where it's just kind of like dumb, like there's just sort of two things sitting next to each other that ends
Well,
up,
no,
or
I
no,
don't.
that won't kill NTP2.
Yeah, I mean, because if you take the disjoint union of an NIP and a simple theory, that'll still be NTP2. Um, but um, I don't know. Does
What about
forking?
like the Urisan sphere? Does forking equal dividing there? The discrete one.
I'm not sure. So probably, I think probably. I bet you this is characterized on forkingequalsdividing.com because Gabe has written papers on the Arizona sphere, so this would stand to reason that he would have characterized that relation. But I don't know. I'm trying just to think of other examples where forking equals dividing. Like, also, I should say that it depends a little bit on what you mean by forking equals dividing,
Hmm.
because there's a difference between forking equaling dividing for complete types and for formulas.
Hmm.
So I think in like the Henson graphs, um, and certainly in a lot of the NSOP1 examples we think about, forking equals dividing for complete types. So if you have a type that forks, it also divides, but you can find formulas that fork and do not divide.
Hmm. Yeah, so
So
Gabe does have forking for equals dividing for the Urisan sphere um for elements, so I assume that means for complete types.
yeah.
At least.
Right. So that it's a different question actually, whether or not it's the same for formulas. And for NTP2, we'll prove it is the same for formulas over models, uh, or over invariant spaces. But yeah, in general, I guess I don't have a good stock of examples in mind of non-NTP2 or non-NTP2 theories where forking equals dividing, or even non-NTP2 theories where I understand what dividing looks like. So in all the NSOP1 examples we know, forking doesn't equal dividing for formulas, although it seems to for complete types. Um, so I guess it's possible in principle that forking equals dividing over models does characterize NTP2 as far as I know, but for formulas.
Okay.
Yeah, it's a good question. Okay, anything else? No? Okay. Well, go enjoy your weekend, and I will see you all Monday. And recall, we have a short week next week, so we're just going to have 2 days. And so we'll do like a taste of NSOP1 on Wednesday, and then we will have lots of time to forget about it. And then Monday after Thanksgiving, we will try to pick up again. All right. So see you all Monday.